Hello guys, welcome back. This is physics lesson number 4. In this video lesson, we're going to start a new chapter. I assume previous chapter was energy resources. We finished it. We did the summary. There was some homework, so hopefully you are doing it or you have done it. But in this video lesson, we're going to start new chapter. It is work and power. Specifically in this video lesson 4, we're going to study work. The definition of work, uh, how to calculate it in specifically in physics. What does the work mean? So we're going to cover about these things. Okay, so objectives, yeah, they define the work done, how to calculate work done, and the work done, the meaning of work done, which is equals to energy transferred. We will talk about that. So how to calculate it, and solve the related problems, related to questions about how to calculate it. It's going to be not very difficult. Actually, whole chapter is kind of review. It relates to energy, conservation of energy, as well as energy resources and energy transfer. Okay, so before we start, this is again a recap, or just take a few minutes, just recall about previous chapters, like what are the advantages of using steam power. So here we want you to think about steam and power, how to generate steam and what's the power, and as well as advantages and disadvantages of steam power. Another question to ponder is, can we produce power without any of the disadvantages of steam? Okay. This is, for you to recall and spend some time. So the steam engine is a machine that changes thermal energy, depending on the temperature, into a mechanical work. Okay, mechanical here word, some work. What are the other machines? Other machines are mentioned in this section, and what are the transfers that take place? Transfers of energy that take place. It's going well throughout this chapter. You should think about this. Okay. All right. As we're talking about the steam engines. So this is a Watt steam engine, and it was the starting of industrial revolution. So the start of industrial revolution, what is the starting of industrial revolution is basically the start of using engines, isn't it? Using engines, gas turbines, specific, and also mass production of high volume goods. Before we couldn't do it before because of labor, because of animals or people. We couldn't do a lot of mass production and high volume goods production. So we start harnessing the energy resources, isn't it? Fossil fuels specifically, like burning coal or burning petroleum oil, to use by using uh, engines to do a work. Okay, so uh, engine as a machine, steam engine, steam machine transfers energy from one form to another form, isn't it? From stored chemical form, like in the form of coal or of petroleum oil, to a mechanical energy or kinetic energy, which is something has got a speed or something turning, moving, kinetic energy. And while doing that, it does a work. Machine does a work. So um, definition of doing work is transferring energy from one form to another form. It's not so in science we have to define specific there's specific definitions for all the words like work. Work doesn't mean in science in physics it doesn't mean go to a job or money uh, or energy. It doesn't mean I feel I run out of energy. I feel I feel tired. There are specific definitions, and in the work case, the definition is the definition is uh, like applying force, um, which will be next slide. Uh, applying force, and moving the object the same direction which is force is applied. So in this case, we are doing work against gravitational force or force of gravity. So we have a small animation here, 1.5 kilogram of a rock. So we are, lifting it. While we are lifting it, my we are doing work against the gravitational force. So I'm applying force, vertical force above, and so I'm doing work. I'm doing work against the force of gravity, and the object is gaining energy. Object is gaining energy. Okay. So the applied force is against gravitational force, and the object is moving at the same direction. So the work done can be calculated. Applied force times the distance, times the distance. Um, so so lifting, you do work to store potential energy as you apply force to lift the rock distance of height. And gravity also does the work. Gravity does the work, converting potential energy to kinetic energy when rock goes down, isn't it? So it is second part of the simulation, the animation. So when the rock goes down, the gravity does the work because the gravitational force is downwards, and when I let the rock go, the gravitational force so uh, pulls the rock down to the earth and does the work. Gravity does the work. Okay, just need to just again forgot to record my time. Okay, all right. So doing work. This is the doing work. Work one more time. Work done is transfer of energy. So any kind of energy transfer, there is a we are doing a work. We are doing a work. For example, in this case, the 1.5 kilogram of rock has got no energy. So I transferred my muscle kinetic energy to the rock's potential energy. So there's energy transfer going on, and that equals to the work done. That equals to the work done. That equals to the work done, and that I can calculate by force times the distance which my object is moved. And the second part, when I let it go, the work done is the gravity is doing work. Energy transfer is the object's potential energy transferred to the kinetic energy, and then it's dissipated to the earth. So this energy transfer going on, potential energy going to the kinetic energy, transferring kinetic energy. And in that case, is the gravity does the work. Gravity does the work. All right. Let's do some of the other. Okay. So another thing is the sign of a work is important. Why it's important? Because it shows It shows what? Um, tells us speed. It tells us the speed is increasing or decreasing. If my work done is negative, then the speed is decreasing. If my work done is positive, then my object is increasing. My object's speed is increasing. Speed is increasing. Okay, so that this sign is important on the calculations. Um, I'm just recapping. So the force and the direction of the movement should be same or opposite, but in parallel to each other. The force applied and the movement of the object should be in parallel. That will give me a work done. To, to do work, my force and movement of that object should be in parallel. In parallel, same direction or opposite direction. Um, yeah. So and the sign of the calculation is important. Right. I think we will learn more when we solve more questions. But let me explain further what I mean by that. Okay, here we have some examples like pushing shopping trolley. When we push shopping trolley, our force is on parallel to the ground, isn't it? On parallel to the ground, horizontal. I mean horizontal. And trolley also moves on parallel to the ground, which is horizontal. So my force and the trolley's movement direction is in the same direction. And in that case, I can say I'm doing a work. I'm doing a work, and it can be calculated the, the amount of force times the distance, how much the trolley moved. At the same time, I'm transferring energy to the trolley, and the trolley kinetic energy is increases. It was zero at the beginning, stationary. Stationary is when there is no movement, there is no kinetic energy. But once I start pushing it, I'm transferring some of my energy to the trolley. Trolley's energy increasing. There's a transfer of energy. If there's a transfer of energy, there's a work done, and work done can be calculated by F times the distance. F times the distance. F times the distance of trolley moved. In the B case is, example, an apple is falling from a tree. In this case, again, the gravity does the work. Gravity pulling apple from the tree. The gravity pulls apple downwards. Gravity does the work. The apple's kinetic energy increases. What does it mean? Well, apple had a potential energy when it was hanging. The potential energy when it is fall, it transferred to the kinetic energy, and the force is pulling downwards. The movement of the apple is same parallel with the force, parallel, same direction. So the force, the work done can be calculated. Force times the distance, the height of the apple's, you know, uh, downward falling distance, height, height of the apple, height of the tree. Yes, you can calculate it. So the next one is brakes, braking to stop a bicycle. Okay, braking to stop a bicycle. Okay, now in this case, uh, when I'm riding a bicycle with high speed, but then I'm coming to the junction or I need to turn. So I'm applying brakes. The brakes produce force of friction, which slows down the bicycle. Okay, now in this case, as I said before, the uh, the in this case, I should my calculation should be negative. My Um, should be negative here. I'm just gonna, sorry, I didn't prepare it in advance. So in this case, my speed is reducing. So the friction does the work, and the bicycle's kinetic energy is transferred to the heat energy internal of the brakes, which got hot. So and my I'm slowing down, and when I calculate it, it should show me the force times distance, isn't it? How do I calculate? I'll calculate force times distance. Force times distance. Um, but my direction of my force is friction, right? Which is the opposite direction of my movement. Movement, friction, opposite direction. So it should be negative times the distance. Um, okay, should give me the work done. The work done, which is negative, isn't it? Which is negative work done, and that means that I'm slowing down. So yeah, the sign is important here, which means I'm slowing down. Okay, let's continue with some other examples. Now, I think we're going to think about how do we calculate the work done. So it says here the heavy objects need a big force to lift it. The heavier the object and the higher it is lifted, the more it is gravitational potential energy increases. So as the applied force and the distance is higher, or as well as the mass, the the size of this the size of work done, the, the the size of force and the distance increases the size of work done. Of course, this is understandable. Okay, from where it's understandable? From here, from this slide. If I increase the force and the distance, of course I will have a higher work done. V means work done, by the way. V means work done. So it means work done. So how do we calculate it? Well, I talked about it. Now let's put it into the with the symbols. Let's define it. So work done equals to energy transfer, and in this case, energy transfer or change of energy, the same meaning. Change of energy, delta Greek. This triangle is delta. In Greek letter, it means change in something. Delta, and here it means change in energy, or increase in energy, like decrease in energy, decrease in energy, increase in energy, change in energy, which equals to the work done. Okay, so as we talked about this, it is affected by the size of force and the size of distance. If my force is higher, then I'll get higher change of energy as well as higher the work done. I will do more work. And the distance is higher the distance, I will do more work. So in physics, please, again, reminder, the work done means not earning money, not like in common language, but it means force times the distance. If I have an object in this here, please pay attention here. If I have an object and I'm pushing it with a force with some distance, half a meter, 1 meter, my work done means F, which is the force applied to the object, and the distance is moved. So I think I have an example here. Okay, we have an example with a crane. So yeah, so that means F times the distance, but the distance, the force and the movement should be in the same direction. Force and the movement should be in the same direction. Okay, let's do example. Solved example, worked example here. So I have a crane. Crane is doing what? Okay, let's read the question. In the question, the crane is lifts crate. Crate is like a container, or you can say as a big box, a container. Crane lifts crate upwards through a height of 20 meters. The lifting force provided by the crane is 5 kilonewtons, as shown in figure. How much work is done by the force? How much work is done uh, by the force? Okay, let's calculate it. Excuse me. All right, I think it's easy to calculate. We have a force here. Force. Okay, so first of all, we need to write down first step by step. That it says in the book, even explains write down what you know and what you want to know. So we know that crane is applying upwards, horizontal, the vertically, the 5,000 kilonewtons, and the distance is 20 meters. So we need to calculate how much is work done. Work done by the crane. Work done by the crane. Work done on the object. Work done by the crane on the object. Okay. So the work done, as you can see here, it is 5,000 by 20, isn't it? It's 5,000 by 20, and uh, we get 100,000 Newton meters. Newton meters, 100,000 Newton meters. Okay, the Newton meters. What does another unit, unit of Newton meters, meaning works Newton meter, works another unit? It's a joule, isn't it? Because energy transfer is equals to the energy transfers is equals to the work done, which is force times the distance. What's the unit of energy? It's joules, isn't it? Joules. Yeah. So similarly, I mean, as the energy of so the work done, unit of work done is a joule. It's a joule. It's a joule. Okay, pay attention. Okay, so we calculated the work done, which is A. Now B. How much energy is transferred to a crate? Crate, is, I said. Uh, okay, so how do I calculate it? Well, the work done, which is F times distance, F times D, equals to 100,000 joules, as we talked about before. That also equals to energy transfer, isn't it? Transfer of energy. So, so, so okay. So the B, the since the work done is energy transfer, is the same amount. So it's 100 kilojoules of transfer. Energy is transferred to the crane, to the box, isn't it? Okay. Okay, let's continue. I think it's understandable. I don't think there will be any issue here. All right. So sometimes there is a force, but because of there is no distance is object is not moved any distance. The work done is force is doing no work. Force is doing no work. For example, when you are sitting on a chair, you are not moving, and that means what? There is a force. There is a gravitational force, isn't it? But it is balanced by the contact force of a chair of the chair, and so but you are not moving, so D is zero, and there is no work done. There is no work done. There is no energy transfer. There is no work done. There is no energy transfer. Okay. Okay. Another example of not doing work. is a spacecraft, going around, or satellite going around the Earth. Now, um, the direction of force of gravity is towards the Earth, isn't it? Like a vertical, towards the Earth center. But my satellite or spacecraft is orbiting around the Earth. So there's a movement, there's a movement, but that movement is not the same direction with the force trying to do a work, which is gravitational force, gravity due to force due to gravity. That was trying to do a work, trying to pull it back to the Earth, but it cannot. So the work done by gravitational force is zero. So, okay, I can just read through it, or you can read through it. Another examples of force that is doing no work is spacecraft is traveling around the Earth in a circular orbit. The Earth's gravity pulls on the spacecraft to keep it on its orbit. The force is directed towards the center of Earth, but there is no movement. I mean, there is a movement. There is a movement. There is the movement of around the orbit, and that movement is right with a right angle, which is perpendicular to the force which is trying to pull it. The movement is perpendicular to the force trying to move it. There is another component of F times D, which is cos theta. Theta is angle between the direction and the direction and the force. The angle between the movement direction and the force. The theta is angle between the direction, force, and the movement. So if it is same direction, it will be 1 because cos 0 is 1. But if it is within the like right angle, perpendicular, then my cos 90 degree, cos right angle, cosinus of right angle will be 0. Meaning this force doesn't affect the movement, and it doesn't do a job, doesn't do a work. So since the spacecraft orbit is circular, it doesn't get any closer to the center of Earth. There is no movement in the direction of the force, and so the gravity does no work. Gravity does the no work. So it says, there is a further explanation. It says, although the force doing no work, this does not mean that it is not having effect. Without the force, spacecraft or satellite would escape into the space and disappear. So because of the gravitational forces, gravitational attraction with two masses, they're on orbit. They're on orbit. They're on orbit. Why they don't fall into the Earth? We'll talk about it later. Because almost my time is up. I just want to finish this with some comprehension check. So there is another work done. This time is against the weight, which is potential energy, which is gravitational force. Okay, you can go through it. There is another question I just wanted to ask you. Here is a ramp. This triangle is a ramp. So there is a box again with a mass. Each box has got the same mass, m. Yol is pushing and moving the box up to the ramp, to the top. But here is a boy. Boy is just moving it vertically. Yol is pushing it to the up. Boy is moving it. So the question is, are boy and girl doing the same work, or one of them doing more work against the force of gravity? By the way, against the force of gravity.